Recorded. Okay, so today I'm gonna talk. Kind of weird. Anyways, so today I'm gonna talk about the natural language processing methodologies to transfer the textual knowledge into actionable item. And I'm mainly focusing this talk on the radiology, but of course I will be touching different other types of clinical notes too that we can use actually to extract information and make the decision based on the extracted information. So I'm an assistant professor in Department of Biomedical Informatics and Department of Radiology. I have also an adjunct position in Department of Biomedical Engineering at Georgia Tech. So before I move forward with our research, I just wanted to tell you or reintroduce you to the 3 pillars of AI. So if you know that the AI, the current advancement of AI that we are hearing from every different parts of the research, actually standing on 3 big pillars: big data, high performance computing, and algorithm. If one of these pillars is not exist, this whole advancement of AI probably will fall down. And big data is one of the very, very important pillar to support this kind of AI advancement, because in 2020, actually, every human is generating 2 megabytes of data per second. So you can imagine how much data they are generating per year. And this whole thing is going digital. So we are actually pumping data into the system, and AI is actually taking advantage of that and learning more and more inferable knowledge from that data to make advanced decisions. And high performance computing, of course, it's getting faster and faster. And it's predicted that in the exascale computing in 2023, we'll have the supercomputer that will be 100x faster, 10x faster than the fastest publicly ranked supercomputer in the world. And you guys are very well known with the machine learning thing, so I don't have to touch the algorithm. Of course, you guys know that algorithm is also becoming very, very advanced day by day. But all these 3 pillars is actually standing on the foundational knowledge of mathematics and computer science, starting from linear algebra, probability theory, information theory, and statistics, of course. This whole deep learning paradigm actually started with the unsupervised feature learning, because even before deep learning, the machine learning existed. But the only problem was, especially for the images, we have to actually hand engineered features for extracting inferable knowledge from any types of imaging. And especially for the radiological images, it is more difficult, because this kind of hand curated imaging or hand curated feature needs a lot of expertise, and experts' time, of course, is very, very expensive. So for example, imagine that we have an X-ray image and we need to predict if the lung mass exists in the X-ray image. So this needs to be processed and extract the information that actually corresponds to the lung mass. And it is not that easy, because, for example, a computer scientist will never have an idea just by looking at the image where the lung mass exists, and if what kind of feature is actually corresponding to the lung mass that would be useful for the prediction. And the deep learning actually changed this paradigm completely, especially the convolutional neural network that can process that images through a multiple nonlinear abstraction and extract information automatically and predict the lung mass. So you don't need any kind of manual feature engineering, and it automatically extracts the important feature and correlates with the lung mass and achieve amazing performance accuracy. But the only big mantra about deep learning is that you have to go large with the training data. If you have very, very small training data, you can never, probably it's impossible to stabilize a large network that can extract meaningful information for your targeted prediction task. But if you need to go large with the training data, you need a lot of annotation from the expert. But who will pay the annotation? Because annotation is expensive, because expert time is expensive. And it's $1 billion business that to create that annotated, curated data set. And industry, specifically like Google, Facebook, they are paying millions of dollars to collect that kind of annotated data set. So especially if you are in a research or academic environment, it's kind of like impossible to pay that much amount of money to curate a good annotated data set for training your very large nonlinear deep learning models. So if I take a step back and look at the data collection process for the AI model development, you'll see that it's kind of like iterative. So it starts with the data collection, where we go in PACS or whatever medical imaging dataset that we have, a database that we have, and we collect the images, we pull the images, right? Then we review the images, and that also needs a lot of time because that needs the data cleaning and everything. But this data review, the data cleaning, the data processing, the data normalization, we can still do it from a computer science perspective, because that is mainly looking at the imaging feature and clean the data, standardize it. But the main difficulty for us as a computer scientist starts from the reader's recruitment and annotation. First of all, the reader's recruitment actually needs a lot of money to recruit the reader and to recruit the experts of the field so that they can do the exact annotation that you need, and to reduce the interdata readability, right? Because if you have a lot of variability between the readers, even if you collected an annotated data set, that data set will have a lot of noisy information, will probably not be useful for your model training. But then the main difficulty is here, that now you have to give the images to the reader so that they can do the annotation. And this is hours and hours of manual job, because specifically if you want to create the outline, or even if you want to create like a image level for your whole study, but still it needs a lot of time from the reader. They have to look at the image, they have to do the particular diagnosis, and other than the image, at that time, they will not have any other information. But in clinical scenario, actually, when they analyze the image and create the annotation, what they do, they will also have all the patient history at the same time, as well as the image, so that they can make a very well-informed diagnosis of that image. But while you are doing the annotation for creating data for the AI model, we usually give the experts only the images without giving any kind of past information about the patient. And that could be sometimes problematic and will create some kind of noisy annotation also. And again, our mantra is still here, that this whole data annotation will need actually, you need to collect a very large annotated data set. But even after creating the annotation of the data set, when we're building the model, we realize that that data set is not enough. So we have to go back and collect more data. And this process kind of becoming very repetitive process. And you have to remember that you need expert labor. It's a very laborious process, it's expensive, and it's never enough. The deep learning, if it's just like pumping the data into a model, right? You always need more and more data for getting a very stable model. But if you go back and look that how the data is actually being generated, that you would see the radiologist, clinician, pathologist, they're actually looking at the images at the same time they're dictating the report, or they're even writing the reports. So it's already, you have the kind of like manual interpretation of knowledge of that image already documented in the report. But the problem is that these reports are actually free text. So it's written in natural language, and most of the time is very ambiguous. So extracting information for those reports actually needs advanced natural language processing technology, so that you can parse those reports and extract the relevant information for creating the annotation for your images, and which is not a very easy task. And it would be even more interesting that if you can actually create a kind of integration between all these different sources to create the information. For example, if you are analyzing a CT head reports and you have a tumor, if you have the following pathology, it would be nice to actually correlate that pathology information also with the radiology information and generate your final level, which is a very, very difficult task in general. But imagine that everything is done. So we have a natural language processing model, and that can correlate all these three defined sources of information to create the annotation. That would be amazing actually for training a machine learning model for this CT image diagnosis, because you will have now correlates multiple level of information and you create the annotation automatically. But the main challenge is that these all reports generated by the clinician, pathologist, radiologist, nursing staff, they are all free text and cannot be directly interpreted by the machine due to the ambiguity and subtlety of the natural language. So mathematically, what you want to achieve is you want to achieve a function around your free text clinical narratives that will generate a vectors. That vector would be a numeric vector, like a numeric embedding of your whole report. So we can use that numeric embedding as an annotation of your image and train it accordingly, because that can be automatically generated from the reports. But then the question comes in that what is the best representation for the documents, so that we can capture the semantics of the text so that the machine understands the semantics properly. And this is not an easy task. There are several research has been done on that particular area to create a semantic representation of the clinical text, or even the semantic representation of the natural language. But in radiology, actually, it has a lot of values that if we can use the clinical text to generate the annotation automatically, because currently radiology is using structured reporting, starting mostly from the 2014. So we have for ultrasound, for liver lesion, we have the lyrates, then we have the BT-RADS for the brain tumors. So we have the ultrasound for the thyroids, then we have the mammogram for the BI-RADS for the mammogram. What it does actually, it uses as less as possible the free text reporting in the documents, and finally it generates a kind of scoring for each of these defined study. For example, you can see that for liver lesion, for ultrasound especially, we have 3 types of scoring. Ultrasound 1 is negative, ultrasound 2 is subthreshold, ultrasound 3 is actually positive, like positive for the cancer. And then for BT-RADS also we have, for brain tumor, we also have this kind of similar scoring. So it's actually the radiologist not only giving you the findings, but also gives a structured scoring for each of the study. So it's immensely helpful that if we can extract the scoring, we automatically get the annotation for that particular study, specifically for the diagnosis. And it's kind of like very interesting. But the main problem is that the structured reporting standard has only been introduced in 2014, but we also have a lot of radiology study done before 2014. And for example, like BT-RAD was just introduced in 2017, 2018. So still the structured reporting is popular among the radiologists, but it's not widely adopted sometimes. And we still have the free text report that doesn't have the code. So if we go back and look at the structured report, you will see the structured radiology reports, they have this particular section. So I'm showing here a liver lesion reports, ultrasounds, and you can clearly see that you have a finding section where they clearly describe the findings of the livers, and they also measure the lesion, also measure and document the measurements. And at the end, at the impression, they also gives you a kind of scoring for that particular liver lesion. So it's clear that they mention the finding as well as they mention the scoring of the liver lesion. So it's very easy from the natural language perspective to quickly extract that labels as well as the finding that is necessary for your imaging. But if we look back and look at the similar kind of report, but in unstructured format, so you'll clearly see that your findings is just like a kind of like text snippet lumped together without any proper findings. So we don't know where are the liver findings, where are the gallbladder findings, where are the kidney findings. So you need a kind of good extraction to extract those information. As well as at the end of the impression, we don't have a standard scoring. So you don't know that what scoring the radiology derived based on this finding. So it's just written in the free text. So it is kind of challenging from the NLP perspective that if we need to access the data from the current study as well as the historic study, there is no easy way actually to use those 2 types of reports and extract the information. So basically what we have to do, we have to derive from the NLP wise, we have to derive a common embedding space where we will be representing both the unstructured report and structured report in a vector format. So probably everybody has probably an idea about the document to vector. For example, like this model in an unsupervised way learns a vector representation of the whole document. So you give the word vectors as well as the paragraph ID. So you pass through the nonlinear layers, and finally in the output layer, you get a document vector. But the problem is that if you just use the out-of-the-box document vector, you would get some representation, something like that the unstructured and the structured reports, they represent in a vector format, but they actually reside 2 different space, 2 different areas in the space, that it clears that the information that is conveyed in the structured report and the information that is conveyed in the unstructured report, it cannot be generalizable, that you need some effective technology so that if we train the model on the structured report, it's also generalizable to the unstructured report. So that is kind of project that we are interested in. So we want to create a large annotated data set using all the radiology study that has been done on that particular methodology or that particular protocol. For example, if we are talking about liver lesion, so we want to use all the liver lesion study for ultrasound, and we want to use both the structured report as well as unstructured report. But the problem is that we don't have annotation for the unstructured report. That means the standard scoring for the unstructured report. So our whole idea is that we will train the model only on the structured report, and we will use all the unstructured report that doesn't have the scoring, and the trained model will be used to extract the scoring from the unstructured report. So what we'll have at the end, a large annotated data set with both structured and unstructured reporting with the standard scoring. So now, if we can automatically generate those kind of reports, those kind of scorings, so you can imagine that we can train a very complex deep learning model without any problem and without automatic annotation. We don't need an expert annotations at that stage, and that will save you time, labor, money, and everything. So our methodology actually combines the natural language processing, deep learning, semantic reasoning, and domain knowledge together in an iterative way again to extract those kind of labels from the free text reports. So we actually have a patent on that. The whole idea is that we are using the free text as well as we are using the NCBO bioportal. We developed a small Sparkle-based system, autocrawler, that goes inside the NCBO bioportal, and given some key terms, it can extract a sub-dictionary for the perfect domain. So for example, if you are working on the liver cancer, you can easily search for the key terms in a corpus of your clinical notes, and then you can query the bioportal to extract the sub-dictionary for your domain. So which will include all the synonym subclass of your key terms and will generate a very comprehensive domain to standardize your space, because you know that structured report, they use a very kind of like templated document, but unstructured report, they use a lot of synonyms. And it has been historic report, so the language changed a lot. So we want to actually normalize the language space in such a way the structured report and unstructured report creates a uniform embedding space. So then we actually developed a report condenser, which is kind of like standard pre-processing NLP step that reads the report, cleans it, condenses it. Then we also have a clever dictionary which stores all the negex related term, the risk related term, the affirmation term, and their synonyms. It is also created through the distributed semantics approach. And finally, we actually use both the clever as well as the domain specific dictionary to create a kind of semantic dictionary mapping. So semantic dictionary mapping step, what it does, it actually reads the free text reports and replace the term with the root term so that we normalize the language space. So once we normalize the language space, we can create the neural word embedding in an unsupervised way. And finally, we can create a context-aware visit vector because we already know the key terms that is we are mainly interested in. So we just look at the key terms and their surrounded area to create the context-aware visit vector. Basically, what it does, it creates the vector representation of the whole report. And now we have the embedding space of the unstructured and the structured report in a normalized way. So in that case, you will not have that kind of situation where the structured and unstructured report will live in two different arenas of your embedding space. So these are the main components, the semantic dictionary generation and unsupervised embedding. So we show the first use case where usually you know that this kind of embedding space has been trained on millions of reports. But what we did here that we only trained on 10,000 reports, and we now tested on 1,188 reports from CT reports from the head. It's for the hemorrhage. And we already see that when we create this kind of report representation, all the high risk reports are clustered in one side of the space. Low risk reports are medium risk report are close to the high risk report, and low risk report are scattered all around the space. So we already know that this kind of semantic embedding even works with a very small amount of data. As well as we also tried the generalization. So what we did is, this is the Stanford data. So what we did, we trained the model on Stanford, only structured and unstructured report from Stanford. We tested on Stanford as well as we tested on Duke. We clearly see that the embedding holds the language space that has been learned on Stanford. It also holds for Duke. And for this case, actually, we outperformed a rule-based system that was actually developed on Duke dataset. So which is kind of interesting. And then we also show the kind of like transfer learning, where we train the model on the ultrasound language space and we fine-tune the model on the MR language space. And we can clearly see that the ultrasound and MR, they are overlapped nicely, and the new words that appear in MR, they also learn the synonyms also from the ultrasound language space, which is kind of interesting. For example, like bright, isointense, hyperintense is also recognized as a kind of like synonyms or similar words of the bright. So which is kind of interesting. And we apply that kind of semantic embedding technology in multiple domains in radiology, starting from CT, MR, ultrasound, mammograph, for different kind of use cases also. And we also did a lot of clinical applications, studied from cancer recurrence, patient-centered outcomes, survival analysis, and we have results for each of these, but I don't want to go into too much detail of each of these case studies due to this time limitation. But I would show you a few interesting results. For example, first is LIDARs, where we actually trained the model again on the structured data, and we propagated the LIDAR score for all the unstructured data. So we actually did it to generate a large data set, annotated data set for images. But what we see that the radiologists, they are also using it to track the patient, because now we, for example, for this patient has started their screening exam from 2007 and till 2018. But only in 2017, actually, we have the introduction of the LIDAR standard, but they have all the reports even before the LIDAR standards will appear. But now we can actually assign automatic scoring. So we can actually track the patient even before the LIDAR standard was established. So you can clearly see that the patient had the LIDAR score 1 till 2016. Suddenly it went to LIDAR score 3. And also for MR, we see the same trend. So it's kind of like interesting that we can track the patient automatically now. And we also did this kind of study where we propagated the LIDAR score for the 10 years of ultrasound screening study. And we show that why the ultrasound missed some of the cases that was actually had cancer diagnosis in California Cancer Registry, but the ultrasound missed the cases because of it was technically limited, or it had a cirrhotic liver, heterogeneous liver, something else. And we also test the generalizability of the model, that we train the model on the Stanford data, we tested on UCSF data, and we clearly see that the model retained its performance. The performance was very high. So similarly, we also annotate the 10 years ultrasound data from the UCSF, and we see kind of like similar distribution as of Stanford for the 3 categories, ultrasound 1, 2, and 3. Then we also compare the NLP model with the radiologist assigned performance, and we clearly see that the performance was quite high for the cases where the patient appeared in California Cancer Registry. We can clearly see that the NLP and radiologist performance was quite similar. So actually the NLP performed quite high for predicting the LIDAR score efficiently. So one of my students actually, he also developed a thyroid kind of like similar approach for thyroid nodule. So, but here the only interesting thing is that, so he also used actually the other types of data, not only radiology reports, he also used the age, gender, race, as well as the clinical indication to create the reports, the automatic scoring for thyroid nodule called ThyRES. And he also developed a graphical user interface where given the nodule description, the model can automatically predict the ThyRES score. So which is also kind of interesting, following the similar idea. And he also tested it on Emory internal validation dataset, as well as a prospective dataset for Emory, as well as on the Stanford dataset, and show that the performance is actually generalizable. So which is kind of, again, very interesting results. So not only radiology report, we also try to merge the radiology report, pathology report, as well as a progress note to create the labels for the recurrence. So we are mainly trying it for the breast cancer recurrence. So we actually divide all the clinical notes of the patient appear in one quarter into the text snippets, and we predict the recurrence for each quarter. So it's not only predict if the patient has recurrence, it also identifies exactly at which quarter the patient had recurrence. So it also extracts a kind of like timeline of recurrence. And we compared that model with the rule-based method that was previously developed and published. And we see the rule-based method actually works pretty well, but some condition that, for example, a tiny metastatic focus, difficult to exclude, this kind of cases where it is difficult to exclude, so it's not confirmed. The rule-based predicted it as distance metastatic present, but actually the ground truth was there is no metastatic because it was not confirmed. But our model actually can efficiently predict that, because, for example, that worrisome of metastatic, you see that this dark color represents the higher weight. So worrisome of metastatic gets higher weight even than metastatic. That means the model can understand the vagueness of the language even. So which is kind of interesting. And similar to our LIDAR study, we also define a kind of timeline of the patient where we read the radiology, pathology, and progress report from each of the quarter, and we are predicting when exactly the patient has recurrence. And we also extracted the text snippet for the recurrence. And now, since we have the recurrence level, we can slice and dice the data set as we want. So we actually first extracted all the tumor grade information and we correlate it with recurrence. We also extracted all the tumor receptive information and correlate with recurrence. And it was pretty interesting to see that the power of NLP, that the whole 10 years database, we can slice and dice as we want. So kind of like interesting approach here. So we also analyzed the generalization of this method. So we took the prospective breast cancer dataset and the performance was still the same, 0.9 AUC. We also validated it on the liver cancer dataset, which was not how the model was initially trained on. And we see the recurrence performance was quite high also on the liver cancer. Then we compare our NLP performance with the cancer registry data as well as the ICD-9 code. So we can clearly see that in the ICD-9, the model actually, the NLP model added more patient compared to the performance of the ICD. Just a second. Sorry. Yeah, so compared to the ICD-9, the model performance was quite high because you can clearly see that the model added additional 474 patients, which was not captured by the ICD-9. So which is kind of interesting that even if we use the standard billing code, it's still actually our NLP model outperformed the standard billing code. So which is kind of interesting. And as I said, that the model was only trained on identifying the distance recurrence, but when we plotted the probability of the predicted probability of the model for the distance as well as the local recurrence, we can clearly see that the model has a high difference between the distance and local recurrence. The model can even understand that language actually represents the local recurrence compared to the distance recurrence. Again, for the liver, we have the similar finding that even if the model is not trained on local recurrence, the model can easily identify the local recurrence. So we just extend the model to also identify the site of recurrence. So once the model predicted is a recurrence positive, so we have a kind of a decision node. So all the no recurrence model we just drop, and that goes to the other 7 defined model to predict bone, liver, lymph node, lung, skin, CNS recurrence. And we see that the model achieved very high performance also for identifying the site of recurrence. That for liver, for breast, we got very high specificity and sensitivity for identifying the site of recurrence. But our main question still remains that, okay, the NLP model achieved the high performance for extracting the annotations, but can we use it for training the imaging model, which was our goal from the beginning, that create a large annotated data set for training the deep learning model. So the first experiment that we did is we curated this recurrence and no recurrence data set for mammogram in Stanford for 10 years. And then we run a very simple CNN model with attention to predict the recurrence and no recurrence. And we compare that performance of NLP curated weekly level data with the manually curated data. And I'm going to show you the results here, that the baseline method is only using all the manually curated level data, which is less than 10,000 exam. We achieved like 0.73 AUC, but then we added more than 80,000 exam with NLP curated levels. So NLP curated levels, they have a high performance, but it's not like 100% accurate, but still we got a huge performance boost when we actually augment the data with NLP curated levels. So similar thing, not only with imaging, we also tried it with predicting the recurrence within the 1 year using only the structured and unstructured clinic notes. So you can imagine one patient has multiple different types of visit, and we want to predict, starting from this time point, if the patient will have recurrence or not. So there can be 2 different situations, that one patient can have recurrence, one patient can not have recurrence. But the problem is that all these patients will have very different heterogeneous types of visit, and those would be like very differently spaced between the visits. So we developed this kind of pipeline, again, following the similar technology that I described before, that we have the text cleaning, but here the text cleaning, the neural embedding training, other than using only our in-house dataset, we are also using some open source dataset like I2B2 Mimicry, and we actually just want to incorporate as much as knowledge as possible for formulating that language space. And then after the document vectorization, we are actually using 3 different kinds of model. So first is traditional supervised, where we're using only the manually curated data. Then we also have highly supervised model, the weekly supervised model, where we are using high specificity, we want to increase the specificity. Then we also have another weakly supervised model where we are using the NLP level with high sensitivity. So these two kind of interesting, because you want to see that how the weakly supervised NLP model can help the model training. Does it need only more data, or does it need more efficiency in the model, or efficiency in the accuracy of the prediction? So that's a kind of like interesting thing. And we trained the model on 8,956 de-identified breast cancer patient data from Stanford. And this is a very simple longitudinal model where we have 2 layers of stacked LSTM, where given each of these encounter representation, we are predicting if the patient will have recurrence or not. So this is a kind of results that I want to show, that the red line actually signifies the recurrent status of the patient, and the blue line actually signifies the predicted probability by our model. So you can clearly see that the blue line closely follows the red line. That means the model has a good trend of the prediction for the recurrence. And this is a kind of like comparison that I want to show, that only using manual annotation, again with a small less than 1,000 data set, we got 0.84 AUC ROC. But when we use the manual annotation and NLP generated annotation together, we had a performance boost of 0.94. And this is the result for the weak supervision 1 and 2. We can clearly see that increasing the sensitivity, we get the good performance. We get more performance boost compared to the high specificity. That means more data, even with less performance, actually, we get high performance compared to the AUC ROC, but the sensitivity and specificity is almost the same for that LSTM model. But then we compare that with the traditional model. We clearly see that traditional model, even using the NLP, performs quite well compared to the baseline, but we had a performance boost with the longitudinal LSTM model that can retain the historic data of the patient too. And in summary, before I conclude my talk, I just wanted to mention 3 important points. The deep learning model, the deep prediction model, works always better with a large data set, even with a weak level compared to the small expert curated data. And NLP tools are very powerful to generate such large annotated data set for medical imaging. And the only thing that we are missing now compared to the literature, that we need the tools to combine the multi-source data for curating the meaningful annotation, because we either depends only on the single source like radiology or pathology or the clinical notes, but the whole field is going towards that direction, that we need to combine multi-source data to curate the meaningful annotation. And that's it. I will conclude my talk here. Please feel free to ask me anything. Thanks.
So I have a simple question.
Go ahead.
Which is kind of brought up in other projects. So why is it that we kind of shifted over to using structure, like the switch to structure report seems to be rather recent? Why is that?
Yeah, I think Judy and Hari can tell better than me, but I can just tell you my opinion that structure reporting, again, it's good that we have a consistency among the language used by the radiologists, so that the documentation is kind of standardized. But if they use very unstructured reporting, you can imagine that these reports will be read by the physicians or the following clinical expert afterwards. And if it is not structurized, or if the documentation is not standard, it's very difficult to extract meaningful information from those structured reports or those reports, right? And that's the main thing, that kind of information is important. And for NLP also, it's of course super important that if you are structured reporting, then for NLP, extracting information is pretty straightforward.
Oh, thanks.
Yeah, Iman's absolutely right. I mean, the main driving force actually is for the referring clinicians. So basically, it makes it easier for them to read